Find the prime factorization of each number: 50, 72, 108, and 143. It's important to be able to factor numbers because this comes into play in several areas, especially with fractions. So let's take a look at each of these. We'll start with 50. To find the prime factorization of a number, we make a factor tree. And so if we look at 50, we could break it down into 5 times 10, for example. There are other options like 2 times 25. You can pick whichever you prefer. Now, once we've done this, 5 is prime. However, 10 can still be broken down. So we do that. 10 is 2 times 5. And at this point, all of the factors, we've broken it down into our prime. So we can write out the prime factorization. Here it's 2 times 5 times 5. Or we can write this as 2 times 5 squared. All we have to do is use a factor tree to break it down and then write out the factorization in the end. Let's look at 72. 72 has a lot of factors, but the first thing I notice is that it's even, so I'm going to factor out a 2. 72 is 2 times 36, and then we recognize 36 as 6 times 6. And then each of those 6's can be broken down into 2 and 3. So if we look, we have 3 factors of 2, 2 times 2 times 2, and 2 factors of 3 times 3 times 3. Or we can write that with exponents: 2 to the 3rd power, because there are 3 factors of 2, times 3 squared, because there's 2 factors of 3. And then this is our answer. You don't have to write both of them with the word "or" in between them. You can write either one, whether you just write out the multiplication or you write it out with the exponents. Either one is acceptable. All right, let's move on. 108. That is a large number, but again, it's even. So I'm going to factor out a 2. It looks like 2 times 54. I'm doing this in my head. You could also actually do the division, 108 divided by 2 to get 54. Now 54 I recognize from multiplication tables. It's 9 times 6. Then 9 is 3 times 3. 6 is 2 times 3. And we've got all prime factors, so we can write out 2 times 2 times 3 times 3 times 3, or 2 squared times 3 cubed. Very good. Let's look at 143. 143 is a lot more challenging. It's odd, so we can't just divide by 2. It's a large number, and it's not necessarily clear what it's divisible by. So what I want to do is I want to start with 2 and work my way up and see what might go into that. Now, it's not divisible by 2, of course, because it's odd. We could check to see if it's divisible by 3, and there's a fun rule for seeing if something's divisible by 3. What you can do is you can take the digits and add them up. In this case, 1 plus 4 plus 3 gives us 8. And the rule for divisibility by 3 says that if this sum of the digits is divisible by 3, then the original number was divisible by 3. In this case, our new number is 8, and it's not a multiple of 3, so our original one is not a multiple of 3. Now, moving on, we don't have to check 4 because it wasn't divisible by 2, so it certainly can't be divisible by 4. 5, it's not divisible by because it doesn't end in a 0 or 5. We don't have to check 6 because we've already checked if it was divisible by 2 and 3, and it wasn't. So it's not divisible by 6. We could try 7. And 7, we can actually just do the division. There is a fun rule for 7 that I'll talk about in just a moment. But 7 goes into 14 twice, which leaves us with 0, bring down to 3. 7 doesn't go into 3. There's going to be a remainder. That's not going to work. It's not divisible by 7. So there is a rule to check divisibility by 7 without actually dividing. And I want to look at that right here. Basically what you do is you take the last digit, you chop it off, you double it, So in this case, 3 times 2 is 6, and you subtract it from the original number, or from, not the original number, from the remaining number. So here we take 14 minus 6, 14 minus 6 is 8, and if the new number is divisible by 7, then the original one was. In this case, 8 is not divisible by 7, which means the original number was not divisible by 7. All right, so it's not divisible by 2, 3, 4, 5, 6, 7. We know it's not going to be divisible by 8, 9, or 10, because if it was divisible by 8, we would have already seen that it was divisible by 2. If it's divisible by 9, we would have already seen it's divisible by 3. If it's divisible by 10, we would have already seen it's divisible by 5. So we check 11, and here I'm going to do the division. 143 divided by 11. 11 goes into 14 once. 1 times 11 is 11. When we subtract, we're left with 3. We bring down the other 3. And sure enough, 11 goes into 33 3 times. And so in this case, we can see 143 is 11 times 13. Those are both prime numbers. So that is our prime factorization.